Molecules with more than one functional group are useful chemical building blocks. Compound D, the structure shown here, is an intermediate in the synthesis of a variety of drugs. We're told that compound D can be synthesized from ethanal, which is an aldehyde, and we need to devise a two-step synthesis of compound D from ethanal, ensuring that we give details of any reagents and conditions required, as well as giving an equation for each step showing clearly all of our organic compounds overall. So compound D, we can see that it contains an alcohol functional group and an amine functional group here. And we need to start from ethanal, which is an aldehyde overall, and it contains a carbonyl bond at the end of the molecule. So what we know about the reactions of our carbonyls are that they can undergo nucleophilic addition reactions. And we can see that the main difference between our structure of ethanal and our structure of compound D is we've added on this nitrogen group towards the end, this amine group. We've got a source of nitrogen and we've now got an alcohol instead of a carbonyl bond. So in order to have gone from the ethanal to compound D, we will have need to have undergone a nucleophilic addition with either some hydrogen cyanide or some sulfuric acid overall in potassium cyanide. And generally, this second option is preferred because hydrogen cyanide is quite a nasty reagent overall. And with this second option here, by using that sulfuric acid and potassium cyanide, we make the HCN in situ overall. So that means that it's made in the reaction mixture, so we're not actually having to handle it itself. So by adding these reagents to our ethanal, what we're doing is we're undergoing that nucleophilic addition reaction with the cyanide ion acting as our nucleophile overall. So let's write out an equation for this, and remembering that our key reagent is the hydrogen cyanide, but that's made in situ. So our key equation is going to be our ethanal. So the structure of the ethanal, we're using structural formulae here to make sure that we're clearly showing all of our organic compounds. Reacting this with our HCN, remembering that our cyanide ion is acting as a nucleophile, and this is added on to our ethanal, and we end up reducing that carbonyl bond to an alcohol and adding on that cyanide overall. And the way that this works is something a little bit like this here. So I'll just draw out the structures to make it clear of the reaction, and we get an attack in here, attack up there, and then the negative oxygen ion there reacts with the H plus from that HCN overall. And that's how we form this compound. So this is going to be our intermediate reaction. So now looking at the difference between this intermediate compound and our compound D, the only difference is between these nitrogen-based groups at the end. So we've currently got a nitrile on the end of our intermediate, and we need to go from a nitrile to a fully saturated amine and carbon-based group here. So to do this, we're going to need to add some hydrogen, and we're going to need a nickel catalyst for this reduction reaction overall. So the equation will be our intermediate of the same structure we drew out above, like so, adding in our hydrogen, our nickel catalyst over the top there, and then we produce our compound D overall for this one, like so. And for this question, we have a mark for our first set of reagents, a mark for our first equation, another mark for our second set of reagents, and a mark for that second equation there. Explain why compound D is very soluble in water, and we need to use a diagram in our answer. So let's start by drawing out the structure of compound D in a more detailed displayed formula overall. So what we can see from our structure is that compound D contains an amine group and an alcohol group overall. And what we know about both of these groups is that they contain lone pairs on the oxygen and on the nitrogen overall. And therefore, because these electronegative atoms are also bonded to hydrogens, these will be able to form hydrogen bonds with water. And because we've got two groups which can form those hydrogen bonds, that means that it's going to be a very soluble compound in that water. So let's draw out some of these hydrogen bonds overall. So we've already added in our lone pairs, and now we're going to start by drawing on the bonds like so. So the lone pairs, you then have your hydrogen bond, and then that's going to a delta positive hydrogen, which is delta positive due to the more electronegative oxygen on there, like so overall. This one. So we've drawn some hydrogen bonding here, and the key thing in our answer is to say that we have two groups which can form hydrogen bonds on our molecule. And the key thing is that it can form hydrogen bonds with the water overall. And for this question, we have a mark for saying hydrogen bonds somewhere in our answer with that water. That's a key thing. It has to be hydrogen bonding with the water as opposed to just within the molecules itself. And then a mark for drawing on each hydrogen bond. We are told that compound D reacts with propane dioic acid, with the structure here, to form a condensation polymer. And we need to draw out a possible repeat unit of this condensation polymer, showing clearly any functional group that's present in the repeat unit. So when it states that we need to show clearly any functional group, this means that we need to draw out our compounds. We can't just write it down in our molecular formula. We need to be really clear with the structures of these compounds. So with our propane dioic acid, this is where we've got a carboxylic acid group at either end of the molecule. And this can react in two places on our molecule of compound D. It can react with the alcohol group here to form an ester, or with the amine group here to form an amide. So we're going to have an ester group and we're going to have an amide group in our compound. So this is from our OH and our carboxylic acid, and this one's from our amine and the carboxylic acid as well. So there are actually two possible repeat units for this condensation polymer. So we can either center it around an ester bond, or we could center it around the amide bond. So we'll draw out both options so that we can see each of those. So let's start by centering it around our ester bond. So what I'm just going to do to start off is I'm just going to draw out compound D in a more clear displayed formula to the side so that we can see exactly where we're going to be forming our ester bond overall. So when we're forming this ester bond, that's going to be bonding from here. So this hydrogen is going to be replaced and we're going to form an ester bond there. So the structure will look something a bit like this overall. So we need to show the whole repeat unit as well. So this is the unit that will get repeated along the polymer chain. And here is our ester group. And then what we've got as well is an open amide group. So this shows that our unit will repeat, so we can put an N there as well if you like to show that it's repeating. And here's our ester functional group in the middle. So this part here was from the alcohol with the amine, so this part here was from compound D. And this part here was from our propane dioic acid, like so. Now alternatively, we could also center it around an amide bond. So instead of showing a split amide bond, we could have the amide bond in the centre, so just slightly drawing this in a different configuration. So this is where we're going to lose a hydrogen from this amine group, and then this will bond with the propane dioic acid there. So it's bonding in the same way, we're just drawing it out in a slightly different way. So we could do it like this, or we could have our ester bond split outside of brackets, and then we could centre our molecule around our amide bond in the middle, like so. And here we've got, this time, an open ester link, and this is the other option you could have for your repeat unit. And for this question, there is one mark available for drawing both the ester and the amide bond. So you need to have both of those in there in order to get that first mark. And then the second mark is for drawing the rest of the structure correctly. Serine, with the structure shown below here, is an amino acid. So that means we've got an amine group and we've got an acid group here and a variable R group at this end here. And for this question, we need to use the electron pair repulsion theory in order to predict the shapes of the bonds around atoms A and atoms B, which are shown in the diagram. We also need to give our bond angles around atoms A and B, and we need to give reasons for all of our answers. So we need to use this electron pair repulsion theory in order to explain our predictions overall. So atom A is going to be this nitrogen atom here, and atom B is this carbon atom I've just circled. So let's start with atom A. So looking at this nitrogen atom, we can see that we've got 3 bonds overall. So we've got a bond to that carbon and a bond to each of these hydrogens here. So that means that that nitrogen has got 3 bonding pairs of electrons. But we know that nitrogen is in group 5 overall from our periodic table. So that means it's got 5 electrons in its outer shell. Therefore, if 3 of those have been used for bonds, that means we've also got a lone pair of electrons on that nitrogen there. So in total, we've got 3 bonding pairs of electrons and 1 lone pair of electrons overall. And therefore, from our electron pair repulsion theory, we know that we've got 4 pairs of electrons in total. So this shape is going to be based off of a tetrahedral, but because we've got a lone pair, we know that lone pairs repel more than bonding pairs. Therefore, our shape is slightly different, and it's going to be a pyramidal shape overall, with a bond angle of 107 degrees, which is slightly less than that of the tetrahedral bonding angle, which is about 109.5 overall. So let's have a look at atom B now, which is this carbon. So whilst we've got 4 bonding pairs overall around this carbon, we've got 3 bonding regions only. And that's because 2 of those bonds are going to the same atom. So we've got that carbonyl bond there, we've got this double bond. So whilst we've got 4 bonding pairs, we've only got 3 bonding regions. And carbon is in group 4, so it's got 4 electrons in its outer shell, which are all used up in these bonds. Hence we've got no lone pairs of electrons. And from our electron pair repulsion theory, we know that if we've got 3 bonding regions and 0 lone pairs, that means we've got a trigonal planar shape overall around that atom, with bond angles of 120 degrees there. And for this question, there is a mark available for the shapes. So in order to get the marks for these shape and angles, it's 1 mark for giving the shape and the angle of atom A. So you need to have both the shape and the angle for this mark. There's also a mark for, again, the shape and the angle of atom B. So you need to have both of these bits in order to get each mark. And then there's a mark there for the explanation of the shape around atom A, and the final mark is the mark for the explanation of the shape around atom B overall. A student adds an excess of aqueous sodium hydroxide to a sample of solid serine, the structure shown here below. The student then purifies this resulting reaction mixture to obtain a pure sample of an ionic organic product. So for this question, we need to draw the structure of our ionic organic compound, which we've obtained, and we need to outline the steps that our student could carry out in order to obtain this pure sample of our organic product from the reaction mixture overall. So our solid serine here, this is our amino acid. And what we know about our amino acids is they've got this carboxylic acid group over here on the end. And because this is an acid, we're going to get an acid-base reaction with our sodium hydroxide, and we're going to form our salt and our water. And this ionic salt is the compound which we need to purify at the end. So this is our donatable proton here from the acid group. And this is going to get pinched by the hydroxide ions from that sodium hydroxide. And what we're going to form is going to be our negative ion. So we've got a negative organic ion here where we've lost our acidic proton from that acid group. We've got a negative charge now on that oxygen. And therefore this forms an ionic compound, so an ionic salt with the sodium ions left behind in solution overall. And we also form water, which I'll just pop in brackets there. So we've formed an ionic solid salt overall. So we're going to be making a salt solution because we've got this salt dissolved in this water. So what we can do in order to obtain a pure sample is we can filter the solution as our first step. And then once we've obtained our solid, we're going to want to recrystallize that. And that's so that we purify our sample overall. And for this question, we've got 1 mark allocated to the structure of our ionic organic compound, 1 mark for saying to filter the solution, and the last mark is for stating that we need to recrystallize our compound in order to purify that so that we get that pure sample which the question was looking for. Tab toxin, the structure shown here below, is a poisonous substance which is produced by bacteria found in lilac trees. And for this question, we need to identify the chiral centres which are present in a molecule of this tab toxin overall. So first off, let's think about what a chiral centre is. So a chiral centre is going to be a carbon with 4 different groups attached overall. So we need 4 different groups bonded, and we can't be having double bonds, so it's not just 4 bonds, it's got to be 4 different groups overall. So let's have a look at our molecule and see how many we can identify here. So working our way from left to right, the thing we need to bear in mind is that this compound is drawn out in skeletal formula. And this is commonly done just so that the molecule looks a bit clearer, especially when we've got larger organic compounds to deal with. But what this means is that we're not going to see any of the hydrogens from our carbon backbone framework. So we can draw these in when we're working our way down if we think we've got a chiral centre to double check. So working from left to right, we've got a chiral centre here because we've got an additional hydrogen. So this is going to be a chiral centre because we've got those 4 different groups attached overall. We've got another chiral centre here. Again, we've got a hydrogen, we just can't see it, but that's also going to be a chiral centre with 4 different groups attached. Now, this group and this group will not be chiral centres because we've got 2 of these bonds going to an oxygen in here. So we've not got 4 different groups overall. So these will not be chiral centres. And this one here was not a chiral centre because there are 3 bonds to hydrogens at the end. So that's the CH3 at the end there, so that can't be a chiral centre. Our next chiral centre is going to be this one here. Let's draw in that hydrogen. We've got 4 different groups, so that will be a chiral centre. We'll mark that with an asterisk. Working our way along, these two can't be chiral centres because they're both CH2s here. So they've got 2 bonds to hydrogens, therefore they've not got 4 different groups attached. But this carbon here will be a chiral centre, even though it's in a ring, because it's got different groups attached either side. Therefore, that will be a chiral centre. Now, the only other carbons we've got will not be chiral. This one, as mentioned, can't be chiral because it's got 2 bonds to an oxygen. And this one here is another CH2, so that won't be a chiral centre. So overall, we've got 4 different chiral centres, and you need to have all 4 marked on with an asterisk in order to get that mark there. We are told that tab toxin can be broken down by alkaline hydrolysis, and we need to draw the structures of all of the organic products of the alkaline hydrolysis of tab toxin. So let's think about where this can be hydrolyzed. So parts of this molecule that can be hydrolyzed will be the amide groups. So alkaline hydrolysis, this breaks down ester and amide bonds. In our compound, we've got 2 amide bonds that can be broken down. So we can split up our molecule here, and we can split up our molecule here overall. Now this will only give us 2 different products, even though we've got 2 splittings, and that's because one of these splits is opening up a ring. So that won't actually form 2 different structures, it just opens up that ring to form 2 chains overall. So let's start now to draw out the structures of our products. So I'm just going to draw them out in skeletal form as we were shown in this question already to make it a bit easier. So we've got a group here, and what we've formed is going to be a negative ion up here. And the reason why is because we've got our acid group, and this proton is donatable. And because we've got the alkaline hydrolysis, the alkali, so a hydroxide ion, is going to pinch this hydrogen here. Therefore, we're going to form a negative ion, which will be some sort of salt overall. We've not been given the specific alkali, therefore it's okay to leave it as a negative ion. So that's going to be our first product. And our second product, we're just drawing from here onwards. So this is where we're going to get our, originally it would be an acid group like this. But as I mentioned, because we've got an alkali, we're instead going to have this shown as a negative ion overall because that donatable proton will react with the alkali. So let's draw in the rest of our molecule now overall. And then for this last bit, we're opening up that ring structure. So we've got an NH2 here where we opened it up from the left-hand side of that bit. And then we've got our carbonyl and another negative oxide ion there overall. And for this question, there was 1 mark for drawing the structure, which is from the left-hand side here, so from splitting up that amide bond for this left-hand fragment. And then there are 2 marks available from the slightly larger structure from this right-hand fragment here. And the 4th and final mark is for having these oxide ions here, so for showing them as negative ions rather than acid groups overall.